Last time we started to address the problem of instabilities and of nonlinear instabilities. Before that, we just observed that we have, let me remind you this, we have the Navier-Stokes equation, and we found a very simple exact solution. Namely, between two plates, you push the fluid, and it forms, in a very easy way, we derived that there is a parabolic profile of the velocities. And it all looks almost trivial. And it is actually trivial to find and to explore this solution. However, the lesson we learned that solution is not enough. We have to study stability of this solution, which means, therefore, it's a very general concept, and you always have to perform this stability analysis in physical problems. Namely, we said that let's suppose we have some this profile, let's call it V0. It's for simplicity we talk about the steady state, but in principle the same would be true in general. So we have some distribution of the velocity, which satisfies exactly the Navier-Stokes equation. In this simple case, it's parabola. Of course, there are plenty of much more complicated solutions. There are people did some very ingenious things in hydrodynamics. But for our purposes, it's good enough. And what we said we have to do is to write down V as V0 of x plus V1 of x and t. Assume that V1 is much smaller than V0. So you can, if it helps you, you can put some epsilon here and consider only the terms linear in epsilon. But you can always put some epsilons, but finally you see that it's just a waste of alphabet. Now, you get a linear equation for V1, and stability is that the statement of stability or instability is that the generic solution of this linear equation may be either it might tend to zero or it might blow up, and we can trust actually the original solution only when it is stable, when this guy doesn't blow up. In this particular case, we actually saw that we can look for the V1 as some amplitude depending on x e to the minus I omega t. And it's basically the question, and as I said, although it would be, it would take some time to do the calculations, you can write down the equation for omega, for A, and derive some relation for omega. And basically the question is whether omega is real or imaginary, and it must be it must be positive imaginary to describe the blow up. And I remind you, I said this many times already, that the reason why the exponential works why it goes through the equation is just that the equation is translational invariant, and this is irreducible representation of the translations. If we were considering not translations, but say a spherical something spherical, we have to use different functions. But in this case, it's very simple. It's just the. But it's all. It also also the important thing is that in the linearity of the equation. It's the reason why this simple solution works so well is that for each omega we have a separate equation for A. Different harmonics don't mix up. They do actually mix up in a very strong way when we go to the nonlinear problem. But in the linear approximation, this is a simple mathematical fact that you always know which functions will or should be used on the group theoretic basis. Doesn't help much with nonlinear equation. And then we said that in the nonlinear case, it is, well, by the way, the first thing to be said is that, of course, its linear equations are very relatively easy, and people did some analytic work for this particular case, and they did some also numerical work. Actually, it's curious, the first analytic check of instability was performed. It was quite ingenious to derive this analytically imagining part of omega, but that was a very smart guy who was 20 years old who was doing this, and his name was Heisenberg. It's something he did before quantum mechanics. Next step is quantum mechanics. You might think that he would start doing nonlinear problems, to build. He actually returned to turbulence in his 40s or 50s, but that was a failure. Quantum mechanics was easier. Anyway, that's just unnecessary digression. The philosophy which people exercise here is that they try to build mathematical models of the phenomenon in the hope that perhaps some general rules for instability can be derived, the rules which are not really sensitive to the concrete equations. And I started to give you some very trivial example of that. I shall repeat it, and then we will develop some much less trivial things. So what I mean by, and that's usually called universality, this fact that there are certain laws which are not sensitive to a particular solution or to or even to a particular equation. And indeed, it's quite surprising and interesting that this universality exists. Actually, it came first not in this kind of problems, but just to give you a taste. I'm still not starting this lecture. I'm still digressing. To give you a taste of what it is. you have boiling water. There is a critical point at certain temperature and pressure. There is no difference between vapor and fluid, and at this critical point, thermodynamical quantities have some very specific singularities. Specific heat goes to infinity, correlation length goes to infinity, many things. With certain, and they go to infinity according to certain laws. There are certain critical exponents, as they are called, in this boiling water, which describe its behavior. Now, you take a totally different system, which has nothing to do with boiling water, a piece of iron which becomes magnetic, and at some temperature you get ferromagnet. Also at this point you get singularities in various physical quantities which are precisely the same as they were in the boiling water. That's a simplest example, and there are hundreds of different systems. You can get what is called critical mixtures when two chemicals started to mix up very rapidly. And again, in many cases, you get the same critical exponents. That was kind of a inspiration. Well, there were, it's hard, you see, historically it's complicated. I will not go into this, I suppose. Although I remember this very well, these stories. I gave you a very trivial example of universal behavior, and that was the universal behavior described by of the system described by this equation. And we said, let's take some function f of this type, and you have 2 points, so that f of x1 and f of x2 are 0. They are clearly solutions of this equation. You can simply say x of t is equal to x1, or x of t is equal to x2, being a constant. And that will solve this equation, because there is no time dependence and so on. On the other hand, if you take initial condition for x somewhere here, the dx dt is positive, so it will start changing in this direction until it hits the x2 point. And moreover, if the initial condition is greater than x2, the time derivative is negative, and you get the fixed point to which all solutions approach. By the way, what would you guess, how they approach, how they behave as time goes to infinity? So let's take some solution. Of course, it would be very easy to solve this equation, but we better explore it qualitatively, because later we will deal with equations which are not solvable, and we need. Tell me, what is the expected behavior as t goes to infinity of some solution with the initial data somewhere here?
Yeah, so it just converges to x2 and then maybe oscillates around x2.
Why do you think it oscillates?
Oh, in case there are other small perturbations.
Let's take a look. The first part was quite correct. Xt approaches the value x2. Plus, let's consider some delta x of t. Delta x of t will satisfy the equation d dt delta x of t is equal to f prime over what in this equation guarantees that that we have a stable solution converging, and how it converges to x2? It's remember that this is a very trivial equation. It's x2 is time. It's a constant, so delta x of t should be proportional e to the f prime of x2 multiplied by t. The stability, or the fact that this small perturbation becomes smaller and smaller, is guaranteed because f prime is less than 0. You see that f prime is less than 0. And that's the reason why x2 and x1 have very different behavior. x1 is not stable at all. There is a solution, but any small perturbation of this solution will draw it to x2. So we have two fixed points, the stable and unstable. That's a very trivial example, and although important, because it tells you what can happen in the nonlinear system. When we say fixed point, it basically means that in terms of Navier-Stokes equation, it means that the solution, the background solution, is time independent. And then we perturb it, and this fixed point may be stable, may be unstable. And okay. And basically, by the way, if the background solution is x1, it is unstable and it tends to a different, the instability takes it to another background solution, x2, which is stable. Now a slight variation of this. You see, fixed points are more or less generic thing when you have first order differential equation with one unknown function. However, if we let's look at the equation which has either, we can write it down in different forms, either having more unknown functions or of the second order. What will happen there? This is an important equation, and the equation is this one. So it's basically, this could be some arbitrary function actually. Basically, if actually it is a minus here, or no, it's a plus here. Yes. So what can you say about this equation? Suppose we are working with very small x. What this describes? If x goes to 0, we get the equation approximately minus gamma x dot plus omega square x is equal to 0. What is this equation about? Except that it's not damped. It's the other way around. Because of the minus. I had difficulties writing plus or minus. My goal was to choose the sign for which at small x it's growing. Okay, and now try to figure out what happens next and how the whole thing behaves. and we will find another attractor in comparison with fixed points.
So if x grows to order of 1, then it'll just be a harmonic oscillator.
Well, yes, and but x begins to grow, and let's suppose for one moment that it becomes greater than 1. Then what?
Then it's damped back.
Back to where?
I mean, at least well, it's certainly damped.
Yeah, it damps. Yeah, that's right. But what happens next? You see, if we started with small x, it starts growing, and it crosses 1. And however, then it starts damping. If it damps it so that that x is smaller than 1, it starts growing again. So, what do you think will be the outcome of this? It's either too large or too small, either too large or too small, but then well, the endpoint, as we will see in a moment, is just that it reaches the amplitude 1 after a while and starts oscillating without damping. It starts this equation, which is called van der Pol equation, describes radio transmitters, and they appeared as an equation described. And so this you have a feedback, positive feedback, which makes the amplitude to grow, but then you have friction, and so let's write it down. This class of equation, let's write it down slightly differently. It's convenient to introduce the complex amplitude A, and A dot. Let's suppose that we have at small a. At small a, we have some oscillations and blow up, some instability. That's what happens schematically when we solve the Navier-Stokes equation in the unstable region. Omega plus I gamma is the frequency which you omega. I assume omega written is real here, but I omega plus gamma, omega plus I minus I gamma is our complex frequency. So this guy oscillates. It's obvious that the solution is just that. And blows up. But we derived it by linearization of the Navier-Stokes equation. If you go to the next term, generally speaking, you will obtain some constant. You have the effective friction becomes dependent on the amplitude, and you get the equation like that, which is more or less reducible to this van der Pol. It's a version of van der Pol. So the basic point is that the basic assumption you are making here is that this was a linear result, but we assume that the damping can depend on the absolute value of the amplitude, and for very large amplitude you are pushed back, like here. If you try to get too much, you will be pushed back to the stationary regime. Now let's analyze this equation. and we will learn some interesting thing about it. Let's change variable. Let's write down the A as a absolute value multiplied by I omega t. And when we substitute it, we will get simply rho dot will be equal to I omega will disappear, gamma as a function of rho square multiplied by rho. But that is the equation of this class. So rho of t, if gamma tends to 0 at some rho, that will be a fixed point for the absolute value of the amplitude. As a result, that's all simple, and I suggest that you exercise, you just play around yourself with this equation. You just invent various possibilities, various equations, and so on. The outcome is very simple. Now we have a complex amplitude A, and which has the modulus and the phase. And there is a special circle defined by this radius. If the solution begins somewhere here, then it's unstable and it starts growing. And can you tell me by now what would be the qualitative behavior of the solution which starts here and of the solution which starts here? Remember, if rho is small, gamma is positive. If rho is large, gamma is negative. It's just that this van der Pol situation. So if it's small, gamma is positive, which means that it will start growing. The amplitude starts growing and oscillating. So can you figure out what will happen eventually? So we have a trajectory which begins to grow, and here the trajectory which begins to get smaller. And this is this special circle, rho star.
So do all points just converge to the special circle?
Yeah, they will wind around and converge to the special circle from here and from here. And this special circle has a name. It's called the limit cycle. It was invented, this limit cycle behavior means that you start generate certain frequencies. And that's, as I said, in all cases when you have a generator, transmitter, they are described by this phenomenon. It was, by the way, invented by Poincaré in the 19th century. He analyzed possibilities. Then it was completely forgotten and reinvented, rediscovered when people started, when radio was a latest fad in 1920s or 19, something like that. Yes?
So in the original equation, is this behavior dependent on your choice of x squared? Or
Oh, no, actually, the only thing which was important for having the limit cycle is that you have some damping which depends on the amplitude. Which changes sign that, qualitatively speaking, you need the mode, you have a mode, oscillation with given omega, which is unstable, gamma positive, it blows up exponentially, but the instability, the increment of instability depends on the amplitude, and it becomes negative if the amplitude is too large. Now, there is a picture of what might happen in the fluid where you have infinitely many modes. The picture is that you first have one unstable mode, then as you increase the Reynolds number, this unstable mode stabilizes, but there's then another unstable mode arises and so on. Well, I probably shouldn't get ahead of myself here. We will discuss it later. In any case, you see, it's all relatively trivial. You have generic behavior of unstable system. It is either fixed point when you have one variable, and generic behavior when you have two variables, or when you have a plane. It's also possible to have fixed points. By the way, that's important So consider some differential equation like that. Let's increase. So when we have this equation, the fixed point was the only possibility. Now, we still have this old fixed point solution is certainly a possibility, generally speaking. We can set f and g to 0, and that would give you two equations for two variables. So you will get fixed points, but also generally for generic equation, another possibility is this attractor called the limit cycle. When you go to three variables, it becomes much more interesting. You still have, again, you inherit all the old stuff. You can have fixed point with three variables. You can have limit cycles with three variables. But then you can have something else, which we will discuss. It's called the strange attractors. But now I want to tell you about much less trivial and much more interesting attractor. Basically, these two guys belong to the 19th century. Now, in the 20th century, something new appeared. Namely, people started to study not only, well, it could be either more complicated differential equation with the more variable, or it could be also a discrete time equation. You can always say that, let's suppose we have some complicated equation, integrated, and then you express xt plus 1 as a function of xt. You have a recursion. That's the simplest recursion relation, which is discrete analog of this one. And once again, I repeat, the basic philosophy is just to see what is possible in general, and then identify concrete physical system with one of the possibilities. We will find some very non-trivial behavior in this case, and it's experimentally observed in some systems. But for that, of course, you need you hope to find universality, that the asymptotic behavior does not depend on the details of this function. Only then it can describe nature. The function which is the representative example is this equation, where f is the function f is just that. And of course, you immediately, at the beginning, everything looks completely trivial. But then you get a big surprise. So let's start with the trivial part. And then I postpone, as I said, it's just what will really be important is just the shape of this thing with one maximum, with zeros here, but the concrete details are completely irrelevant. So let's start with finding fixed points. What are fixed points here? How would you approach finding the problem of finding fixed points for this evolution?
So
Give me some simplest fixed point here. There are two fixed points actually. How you do this? When you have this, when you are given this equation, what is the equation for the fixed point? Let's call the fixed point x star.
So you want xt plus 1 minus xt equals 0.
Yes.
So that implies f of xt equals.
Yeah, that's the equation for the fixed point. The fixed point here, we just have to solve the equation. And there is one obvious solution. Yes, 0 is a fixed point, but it will be a trivial fixed point, which is not interesting. But there is also one more fixed point, because we have 1. Let's divide by x star. We get lambda x star. So we get 1 minus 1 over lambda. Am I right? Yeah. And that will be the other fixed point which we will be concerned with. It's very easy to see what it means. Let's just, this is the function f, and let's just take a straight line, which is x star divided by lambda. And when this, so they cross at x equals 0, and at x, this is x star equal to this thing. And that's basically it. Okay, now from what I said before, we found the exact solution of this evolution equation, which is just a trivial fixed point which we encountered before. What should we do next, according to what I have said before? What is, if we believe that it describes some physical system, what's our next step? After finding fixed point is like this laminar solution in hydrodynamics. Yes, we have to study stability, linear stability. How we study linear stability? Very simple. We just say, let's take xt equal to x star plus delta x. Delta x is some small perturbation. And we have x star plus delta xt plus 1 equal to f of x star plus delta xt. I remind you, x star does not depend on t. It's a steady state solution. And this is equal to f of x plus f prime of x delta xt. Now this cancels, so we get the equation. So far, no surprises. it's just mimic the same thing for continuous equation. Delta xt is equal to f prime of x delta xt. Now, what is the stability or instability condition here?
If the derivative is less than 1.
To be precise, you are right, but to be precise, its absolute value should be less than 1, because in fact derivative is negative here. And that will be quite important. So let's check. As I said, it took Heisenberg to explore stability in the Navier-Stokes equation. Here we can, any high school kid can do this. We just look at the function f, which is lambda x minus lambda x squared. F prime is lambda minus 2 lambda x. So f prime is lambda minus 2 lambda 1 minus 1 divided by lambda. I don't know if I make a mistake here. Lambda, so we have minus lambda plus this gives us 2, right? So the absolute value of this thing, and we have to have stability is minus lambda plus 2, should be greater than minus 1, or lambda should be smaller than 3. So if lambda is smaller than 3, then indeed our fixed point is stable and nothing happens. But the loss of stability, lambda is like the Reynolds number in hydrodynamics. At the value 3, the fixed point becomes unstable. F prime at lambda equals 3, f prime at x star is minus 1. And then it becomes more negative than minus 1. All right, so we now have to figure out what happens at this point, at the point lambda equals 3. And what will help us is this equation. How it behaves, what happens to those delta xt, how they behave when the derivative is minus 1. Well, you see, they, roughly speaking, they are not growing yet, but they behave like minus 1 to the t. So the impression is they are not, and then these two, you see that the behavior of even and odd moments of time is different. So the system begins oscillating between even and odd moments. So we want to explore these oscillations, and the picture is this. We have x star we expect that there will be 2 points, x1 and x2, corresponding to even and odd thing, and the system will start oscillating between the two if lambda is greater than 3. Then, well, I will probably tell you the answer, and then we will derive this answer. The answer is relatively easy, but some features are quite, well, further features will be fascinating. So the picture which we will arrive at is that we have the stable, if we just cross 3, we will have the stable solution which is called the 2 cycle. The system is just jumping from one point to another and back. This will become unstable as lambda is increasing at some point, 3 point something. And instead of the 2 cycle, we will have 4 cycle, and so on. And finally, at some value, I think 3, in this case, it's completely irrelevant, the concrete value of lambda. At some value of lambda, there will be infinite cycle here. The system will behave in a complicated way. So let's try to understand this and derive this. This phenomenon is called period doubling. And by itself, it's not such a surprise that we can have this. What is surprising is that there are several universal features in this case. Namely, well, I can just give you, to make things interesting, I will just tell you the highly non-trivial fact, and we will derive it later. You see, you have certain values of lambda n at which you have 2 to the n cycle. At lambda n plus 1, you have 2n plus 1 cycle. Now, one of the amazing, there are several quite amazing things here, but they become closer and closer, and they behave like certain constant delta to the power to the n, and this delta, which is, it's a completely universal number. It's the number which is approximately 4.67, and it's a new constant of nature. Namely, whenever it has nothing to do with this pathetic function, you know. It's just completely general. When you have transformations like that, you can try, for example, that's the way, by the way, how it was discovered by Mitchell Feigenbaum, that by playing with calculator and using different functions here. You can have some sine square function. You can have any function you like, and this is the first, this will be the universal law. Now, even more surprising, there is period doubling occurs when you have a fluid between 2 plates with different temperature. There is convection, and this, by observing this convection, people found that convection becomes, steady state convection becomes unstable. It doubles, and there is a sequence of period doubling, And believe it or not, these temperatures at which to n cycle, 2 to the n cycle becomes unstable, governed by the same equation. So it's quite fascinating, and I will try to now to explain where it all comes from. Although we will not have time, of course, for the detailed exposition. And that's not all. Actually, you can say that you can take these functions. What we're considering is iteration. When we go to large T, xt is something f of f, and so on. Turns out that independently of concrete function, the resulting iteration tends to a special particular function, which is independent of where you start from. It's completely universal again. So it is just amazing thing. When you iterate, it doesn't matter what you iterate, but when you iterate it long enough, you will approach to something universal. And in nature, you find these things. So the statement is, whenever you find in nature, it's not that, you see, period doubling is rather special situation. It's not that, it's rather rare, actually. But if you find it, then it will follow this. There are several universal laws which it will follow. So let's try to understand it somehow. Let's try to understand the first step here. Well, the first, so we began with a fixed point, and we already know that at lambda equals 3, it becomes unstable. And it starts jumping to and fro. So we would assume that there are 2 points, x1 and x2, between which the system oscillates. What is the equation for these 2 points? I remind you, the equation for the fixed point, for the original fixed point, was this. But this equation became unstable. This solution became unstable. Now we have 2 points and 2 cycles. Tell me what the equation, how to determine these values. Yes, please.
So x2 equals f(x1).
Exactly, yes. They are determined by this equation. And as we will see, at as lambda becomes equal to 3, the solution appears. It is not present there for lambda smaller than 3. The convenient way to treat it is to introduce the function f2 of x. Let's introduce the function f2 of x, which is f of x. So in this case, this function f2, it has those x1 and x2 becomes fixed points. You see that f2, say, of x1 is f of x1. It's f of x2. And this is x1. So it's all quite simple. So it makes sense to study those 2 cycle points. They are actually fixed points for the iterated function. And that's how we will be dealing with this, not by looking at the points themselves, but by introducing higher and higher iterations of this function. So let's take a look at what this function is. And by the way, if we consider fixed point, of course, there is also the third point, which is just the same x star here. It didn't disappear. You see, that's what I want to stress here. It didn't disappear because we still have the solution. This solution is still there. It's just like with this laminar flow. The solution is still there, but it is unstable, and the physical solution is the two-cycle. Instead of fixed point, we have the two-cycle. But the remnants of unstable fixed points, they are still there. They are still between those physical points. Okay. If we started with this concrete function. It was second-order polynomial. Now, what kind of thing is the function f2? What kind of function is this?
Fourth order.
Yes, it will be some fourth-order polynomial. And not surprisingly, with the order 2 polynomial, we had roots. The number of roots was 2, which and one was x equals 0, and which we simply dropped. So we looked at this picture. We had this, and these are two things. It's clear now that for the fourth order polynomial, we can have what is the situation with roots for the, if we have the equation, we now look for the solution of the equation x equal to f2 of x. What can you say about it? How many solutions in the first place? You just said that it's the fourth order polynomial, so yes, one of them is again x equals 0, which is completely trivial, but actually we can have. You are right. It's there are 3 non-trivial fixed points corresponding to 4 solutions. But what else? How would you, when you have solutions, can actually there could be smaller number of solutions, right? 4 is, as you said. So what are options? If you have generic fourth order polynomial and looking at its roots, what would you say? What are possibilities depending on the coefficients of this polynomial? You said at most 4, and it was quite right, but then what can happen to the roots of the fourth order polynomial?
They can be complex.
Huh?
They can be complex.
Yeah. What can happen is that so how many real roots will remain? Huh?
Either 2 or 4.
Yeah, it's either 2 or 4. Okay. If we remove from this, so just to. If we have a complex plane, we generally have four roots. what happens to them when then they become two roots only? How they move when you change the coefficients of the polynomial? What is the typical, what kind of disaster can happen to them? Yeah, please.
These two.
Well, what can happen is they collide and go to another world. And that means that we have either one fixed point, or we have three fixed points, depending on the coefficients. Okay. So what is the regime with one fixed point? It just describes the stable region here. When we have the regime with three fixed points, these are three fixed points. So more diagrammatically, what happens is if you we just calculate this thing. You see it's just lambda f1 minus f, lambda square x, 1 minus x, 1 minus lambda x, 1 minus x. So I iterated the function. And if you look at it, it will have the picture will be something like that. And these are the 3 points I was talking about. We can actually by the way, and this is the regime corresponding to the 2 cycle. And how it looks if we return to the steady state, to the 0 cycle. As you said, here we have, these are roots of this 4th order polynomial. So we have this equation and the 4th order polynomial. It's we have these 4 roots as it should. Now, what diagrammatically, how on this picture what will correspond to the region where you have only 2 roots instead of 4? By changing parameters, you get, yeah, please. That's right. If you just push this line down, you will have only 2 roots. And that's precisely, you can check, this precisely corresponds to the collision of those roots. Okay. So we see that things are, we see how to, we can now calculate and see that these two fixed points are stable, while the middle fixed point is not. Once again, how we do this, we simply, to judge the stability of these fixed points, we have to calculate f2 prime of x. And calculating f2 prime is not difficult. It's f prime of f of x, f prime of x. And so at the fixed point, you see it's just f prime square. In this way, it's I will not go into this elementary analysis. In this way, you will see that that for lambda lambda greater than 3, for lambda less than 3, we have only one fixed point. For lambda greater, we have 3. And you can, using this formula, it's very easy to see that this is unstable, and that's because it goes too steep here. And these 2 points, these 2 fixed points are stable, and they form the 2 cycle. And in this way, we actually go to more and more complicated things. And we introduce the function f to the n of x, which have a huge number of fixed points. So we have 2 to the n cycle. And then the first numerical observation, which turned later into the analytic observation, is that this scaling law here, that we have exponential convergence. And moreover, the picture becomes, the polynomial becomes very complicated, and the distance between the 2 fixed points, say between the point, the left fixed point x1 minus x2, it of course becomes smaller and smaller. And the result of iteration, well, I actually can only tell you this much, that you can find the limit of this function as n goes to infinity. And it introduces a new universal function, which doesn't, as I already said, it does not depend on the concrete original function. Here we iterated some concrete function, but that doesn't matter. Any function of this type with one maximum and with zeros at 0 and 1 will give the same result, which is expressed in terms of the function of the universal function g, satisfying and very interesting functional equation. I'm not saying that it's not precisely right that this function converges to g, but you have to rescale x. I don't want to go into those details. But the very beautiful thing is that you finally get this equation from which you can numerically determine alpha. Alpha is like an eigenvalue. You need to, for having the solution, you need a particular alpha. Otherwise, it doesn't have a solution. It's a completely new equation in mathematics. And you find alpha, and you also can find delta by some tricks from this equation. And as I said, in a number of physical situations, you can check this. You check those exponents. The most important part, this is a very beautiful and intriguing part, but that there's a universal equation. Notice that this is equation for any initial function f. I can't stop stressing that's how surprising this is. And at some lambda, we get infinite cycle. But this significance because it doesn't. It's not chaotic behavior. The same equation will have chaotic behavior after period doubling ends. So period doubling is not chaotic in the sense that if you change a little initial data, the outcome doesn't change, it changes also a little. There's no instability. Chaos, as we already said a few times, is what is called sensitive dependence on initial conditions. And it's not here. So, but what is amazing, some simple case of chaos is in this equation, but beyond this period doubling. And I will tell you now, maybe I still have some time, yes. Of course, as you see, to explain this completely, it will take quite a few lectures, which we don't have. It's a lot of non-trivial mathematics, and mathematicians did some, they found a lot of subtleties here. But those subtleties are not very important for physics. For physics, what is important and to be remembered is that three things. Period doubling is universal if it occurs, and governed by the scaling exponent, which are new constants of nature, so to say. But as I said, there is a much it's surprising, but the much simpler regime takes, when you go at some critical lambda, I don't remember in this case what it is, you have infinite cycle, and then regime changes. And people, of course, studied it numerically. It's a very simple and nice exercise for numerical analysis. But what is quite amazing is that for lambda equals 4, you have an analytic solution of this, which displays chaos. And I will show you how. Let's take this equation and rewrite it in the following way. Let's introduce xt then we have 1 minus ut plus 1 divided by 2 is 4. 1 minus, you will see why I'm introducing these variables in a moment. 1 minus ut divided by 2, 1 plus ut divided by 2. So we have 1 minus ut square here. And this equation actually is almost trivially solved by what do you think is a good substitution which will help us with this equation? Yeah, exactly. Good. It's indeed, when you have such combination, you always should try some trigonometric functions. So we have, if ut is, say, cosine phi t, we have here sine phi phi t divided by 2, phi t plus 1 divided by 2 square equal to cosine to sine phi t. And we get a very trivial solution at the first glance. Phi t plus 1 equal to 2 phi t. Now, nevertheless, this solution is chaotic. And the statement which I'm going to make is that the x variables, the original x variables, are randomly distributed. You can calculate, it's an ergodic system. And we can calculate any ergodic average. So you take arbitrary function phi of xt, you take time average, and the conclusion is where xt is a solution of this equation, and the statement is that as t goes to infinity, it tends to a particular, there will be dx square root of x1 minus x. This is the probability distribution multiplied by phi of x. So this is a probability distribution. So you are able to replace time average by the concrete. This is the, for this toy model, it's the analog of the Gibbs probability, or Boltzmann-Gibbs probability. So it looks quite amazing. So by the way, I should use this letter. It has nothing to do with this angle phi. So why we will we have a circle. Why I'm saying that this system is, although it's completely trivial, it is chaotic. What happens? What is special? There is one thing which I did stress here, namely that it is modulo 2 pi. You see, without this, the trivial solution is simply phi t 2 to the t. But when you take modulo 2 pi constraint, it means that you start with some initial value here, then it jumps here, 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 and here, and then the picture becomes more and more complicated. The key point in this is that, well, the key point is that two close by initial data will diverge like 2 to the t, but you don't have, you have a compact circle on which it all lies. As a result, this compact circle will be covered homogeneously with the points. Well, I will tell you more our next time. Let's stop here.